And so in this case, we want the same state machine, but they don't have the same log. And that's what I'm having trouble with. Like if
So-
they end up in the same state, but don't see the same sequence of events.
But they see the same sequence of events for each.
The constraint is, I haven't gotten into the state. So you have the log, and then you have the state is a thing that I'm deriving from the log. So I'm clearly separating log and state.
How do you reconcile log and DAG and acyclic graph, like in your here in your model? Like, what's the difference between a log, a sequence of timestamp events, and a graph where you have forks in the road? Like
There is no sequence.
Get log.
Yeah, I don't have a B, C, D, E, F. This is the log. The log is a graph.
Yeah.
There is no linear version of it.
So it's a partial order or whatever.
Yeah.
I suppose. So in the same sense with relativity. So
so the child-parent relationship here means happened before, though.
Yes.
Yeah.
Yeah. Okay.
So the arrows are happened before, but siblings don't have a happened before.
Yeah.
Like they have different timelines, basically.
They have an ambiguous timeline.
So an event that's happening for Bob here influences Alice out here, just because of how it gets shifted or whatever. But then, so let's say, so Bob, instead of just having one event each, we can have Bob and Alice have 2 events each. So an earlier one and a later one. And this is actually somewhat relevant because they happen to fall on each other's causality graphs here. So this event, causality, causes something to happen for Alice. So in a sense, Alice sees that thing happened. So that, because it sees it, that means that, you know, now you have the ability to have been influenced by it in some way. Because otherwise you wouldn't have the ability to be influenced by it in any way.
Like you saw a supernova explode.
Yeah.
And then you started dancing around because, oh my god, supernova exploded.
Yeah, yeah, exactly. And so the thing is, you couldn't have started dancing around because the supernova exploded here, even if it happened in some sense after, like, the supernova exploded, because you were far enough away from it that you couldn't have seen that.
The light couldn't have reached it.
Seeing that's important, not.
Yeah.
Yeah.
And the distance.
Yeah.
Like how far.
Well,
Yeah,
no,
yeah, it's the relationship
So,
between time
if
and.
the supernova is 2 million light years away from you, even if in some sense, so if it's 2 million light years away and it exploded 500,000 light years ago, or half a million years ago,
Yeah.
then in some sense you can say that happened in the past, but the light cannot have reached you yet.
Yeah, there
So-
is a place for which that has happened in the past in which you have not seen that yet.
So one explanation I've read that does much more intuitive understanding is, say, the supernova exploded, but you're moving away at
Yeah.
light speed.
Yes.
That means the light from a supernova will never be able to reach you. So actually it doesn't matter whether you started dancing before the supernova exploded or after, because that sequence doesn't matter because the light will never reach you.
Yeah,
So-
yeah, if it's moving away for you at
Exactly.
the speed.
Basically.
Yeah.
So
That's
even
the
though it
divergent
happened in
timeline.
the past for you, it's going to be in the future.
No,
If you're-
so-
You won't ever observe it.
If it's 1 million light years away and
It's
it
so
happened
fucked up.
500,000 years ago,
Yeah,
there is
relativity.
a frame of reference in which it happened in the future.
yeah, so not your frame of reference. In your frame of reference, it hasn't happened
So
yet. So
there-
you
there-
haven't seen it yet, but there is someplace else in the universe that has seen it,
Yeah.
and it will probably see you having not yet seen it before.
Well, so there is a theoretical spaceship moving through space fast enough in a certain direction that it sees you dancing and a supernova happening, and there's a different one that sees the supernova happening and you dancing,
Yeah, yeah, the order can be swapped because of.
depending on how fast
Yeah.
you're
You're able to
Well,
witness it or to observe
No,
it.
because if anybody was able to see you dancing before the supernova, then we know for sure that it wasn't causally related. Yeah. It can't go that way.
Okay.
Yeah.
So, there is one issue though, because one assumption underpins that, because we're on the relativity, is there is, in the relativity or in general physics, there is no information loss. That's why black hole is such a big problem, because it says information regardless the motion of reference will eventually get there. But in your system, that is not guaranteed because a permanent loss of a packet will break that underpinning assumption.
No, I
Because you
think so.
cannot, because
Okay.
your requirement is there's no synchronization, which means no state sync.
Wait,
You can, the loss is irrecoverable.
I need to talk about some other stuff first.
Okay.
Yeah.
So, okay, I'm gonna jump over to the, oh, now we're on the same screen. Okay, whatever, the presentation is not set up for this talking with it. But you have a log, the log is the graph. And then separately, you have state. So this is how it's structured. So you have what happened, the order in which it happened. And you have state representing the current picture. So we have various different peers. We have a list of peers. We have a list of this person trusts that person. We have a list of accepts and who's ticking and blah, blah, blah. The actual details won't make a whole lot of sense right now, but there is a picture of the current state. The constraint, the invariant is, no matter who you are, if you have two nodes and they have the same subset of the graph. So if Alice and Bob both see this set of events, then the critical constraint is that they must therefore have the same picture. When they play these events, when they build this state, then they must have the same picture. If they don't, it's a bug. There are bugs. But that's the plan. That's how it's supposed to work. So whatever your current set of events is, then you can build a picture from that, and two people with the same set of events will agree on that picture.
Then depending on the order of arrival of events, you might need to roll back state.
No.
So I'm very, very, very careful that it doesn't matter. The data structure and the way the state and the way that state evolves is very carefully written so that it doesn't matter what order those sibling events are processed in.
Yeah.
Which is why I have a lot of bit feeds.
Yeah.
So if Alice accepts Bob and Bob accepts Alice, those are stored as two separate bits in the bit matrix. And so it doesn't matter which one you execute first. If you execute both of them, you will arrive at the same state.
Okay. Yeah. So you can't do arbitrary stuff with it, but you can be very particular with what you do and do not allow.
Yeah.
And you could have a lot of things, and maybe it's enough that you can do with this. But yeah, you can't do arbitrary things with
Yes.
that stuff.
Yes, this is not, there's a lot of constraints.
Can you give an example of something you can't do? Something that's arbitrary?
No, I don't want to type in my password, shut up.
Well, so an example, so this is a very, very toy example, but let's say that what you were trying to do is you're trying to count up to a really big number, and everybody is proposing another number that we're gonna add. And so like, they just throw in another number, and we'll say that you have arbitrary precision, natural numbers. You don't have negatives, you only have natural numbers, and only get bigger. And so you can keep adding and adding and adding, and that won't change anything. But let's say instead, so that would be an example of something that doesn't matter which order the thing comes.
So basically
You
like
have-
reduce, map reduce, like you can
Yeah.
reduce the operations,
Yeah.
they are additive.
Yeah, but let's say instead you had some operation which is fundamentally not commutative. And so then it gets into a weird thing, so let's say floating point numbers. So while you're gonna have to trust me on this because explaining all the specifics is a little complicated, but the order in which you perform your operations with floating point numbers very much matters. Like you can't have.
Because fundamentally there's rounding.
They have finite precision.
Yeah. Well, it's just they're not in a sense it's not doing addition, subtraction, multiplication, division the way you think. It's doing a different thing that kind of approximates what those things would look like a lot of the time, but it's doing a different thing. And the thing that it's doing is not commutative. It's not associative, you know, and so by getting rid of having some operation that is not necessarily associative or commutative, it matters what order you do them in. Then,
So,
yeah.
This, you can't do arbitrary things in the sense of this system does not allow, this will not work. This design will break down if you start to do things that aren't commutative. If you start to do these kinds of transformations, then all of this breaks. So what I did is I said, okay, I'm gonna have this causal graph, I'm gonna have this Git history, basically, literally what I was thinking. And then I'm going to build a state based on it. And that state, the way that state evolves, and the events are things like, we connected, I accepted Bob, we started ticking. So the events are pretty simple. The actual events I'm using in the game are not that complicated. How I'm processing them, how I'm storing that state has a lot of constraints on it. The way that works out is I've decided, okay, I need these events, this is how the system's gonna work, I have this log, I have these constraints, I'm looking through the code and I go, oh crap, that's a bug. Now I have to figure out a different way of doing it.
But this works because the type of events you have can't conflict with each other, because if there was some possible contention, I don't know, there was some space in the game that two players can't occupy at the same time. If player A occupies it, then that's an issue.
This is the multiplayer engine. This is we all agree to hang out and play a game together. The actual game logic is in its own bucket, and basically once we start playing the game, then we have to be in lockstep. Then we have to be synchronized. So there is a synchronization point in this graph. There is a point where you say, hey, we're gonna play, now we're synchronized, and then there's a whole different set of constraints to make sure that you're doing things in lockstep.
And this is just to get that deterministic lockstep agreement among all the players.
Yeah, basically.
Yeah, okay. So that's why your events are really simple, like, we accepted each other, we started ticking. Okay, because you're not gonna play the game on this graph.
No.
No.
No. The gameplay does not happen on this graph. So I'm gonna talk about the log a little bit.
But how would you handle a permanent loss of an event?
Okay, so if I receive an event, okay, I'm gonna resolve
Basically,
this because
some member did not receive some event.
Okay, if the system detects, this is not actually a thing I've implemented yet, but the idea is if the system detects that somebody has disappeared, then everybody else says, hey, this person is gone, and they kick them. So in a permanent loss, as in this guy's computer exploded, everybody else says, hey, we haven't heard from him in X amount of time, we're gonna drop him. For a temporary loss, this packet went poof. So, you know, Alice has some series of events, some things are happening, and Bob is doing a thing, and maybe I should, whatever. And, you know, there's some relationship between these two. If Alice receives some event,
Basically, the situation of not just out of order, that may appear some out of order, but perpetual, because you don't receive the previous one, but you need the previous one to move on.
If Alice receives some event from, that shouldn't be a thing there. If Alice receives some event from Charlie, if Alice says, hey, I have this event, it has prior history, I don't have that prior history. Alice says, okay, great, this is going off in a bucket. And in the processing loop, Alice says, hey, I need this thing, which you'll have an ID for it. You know, there will be an ID, because, you know, you hash the message, you have an ID. And then you list the parents, and the parents is an array of hashes. So Alice receives Charlie's event. That event says it has a parent.
Right.
Alice says, I need that. So she goes and interrogates Charlie. So assuming that Charlie hasn't gone poof, assuming that Charlie is behaving properly, Alice will eventually get all the prior history of that event. If she doesn't, then Charlie gets kicked.
But isn't that a synchronization, Alice synchronization with, event synchronization between Alice and Charlie though?
Synchronization in the sense of git pull, in the sense of we all have the same set of events. yes,
Yeah.
there is a synchronization process.
Right, because that's what I was trying to, get at, because you said requires no synchronization, but in this particular case, you have to synchronize. For example.
It's not synchronized between, Charlie and Bob.
Right, no.
So Alice could get all of Bob's stuff
Yeah.
and then later get all from Charlie.
Correct. For example, a situation, Alice received a request from Charlie, and Charlie said, I'm sending you this message because Bob broadcast a message.
Yeah.
Alice says, no, I never received Bob's broadcast, that's why I cannot process Charlie. At that point, if Alice attempts to retrieve the lost state from anybody, that is a synchronization process trying to recover previous events.
Yes.
Because that's.
That
right?
kind of synchronization happens.
Okay.
So it never makes an attempt to guarantee that everybody has the exact same set. So it does not say, I have all of these, do you also have all of these? That is not a process that happens. What happens is, WTF, there's a parent missing, give me the missing stuff.
Yeah, but in the strict, special case that your entire event chain is strictly linear, then you essentially do have
Yeah.
that, right?
You can, well, yeah, in the case where there's not a whole lot of things happening and you're not generating a lot of history, yes, you should all arrive at the same state. You should end up being synchronized. So it should be normal to reach a state where everybody has the same graph. The system does not require that, but that should be a thing that happens.
In a case like that.
Yeah. Yeah, unless you're sending
Nobody's-
stuff all over the place.
Nobody's waiting for that to happen in order to take some action. But eventually, regularly, it happens.
There is no, you don't wait for full synchronization. You only wait for, do I have the history of whatever I have, whatever I'm executing. And if you don't have the parents, it doesn't get executed.
How do you manage the networking discovery and stuff? Like how a peer knows about other peers and how do they communicate? Like is it all to all?
I don't, right now.
That's what he's working on. That's some code for it.
Making the state machine work comes before that.
Yeah.
Getting rid of all the bugs and making the log and the event processing, yeah, that's a later task.
Okay.
So, you said you never have the situation where you have to rewrite history to like insert something into the tree, but you're doing that just by never writing the complete tree until you get it all. Right? So you've got the missing thing,
okay.
you need the missing thing first.
Let's talk about the log and then I'll talk about that.
Okay.
So you have a log, you have a list of entries, you have orphans. That's the synchronization part. So here's a list of and this is probably the parent ID, whatever. Point is, you have a list of, I can't do anything with these yet because they're orphans. Entry is this data plus a signature, and the signature implies who it came from. You have parents, and you have the actual event itself, and I'm using generics and making it generic because that's just how I like doing things. Attached entry is just a little convenience to plot things together. You have parents and children. So parents here is IDs. You have parents here that is resolved to an actual entry. So it caches that lookup basically. Generation number is, this is generation 0, and then this is generation 1, blah, 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 for ordering. So to be able to iterate over the graph in a, given here are the things I know about, to be able to iterate over that in a deterministic order, generation number, message IDs, just sorting, topological sorting. This isn't super interesting. Get has all add. When you add, you check if it's an orphan. You plumb up all the stuff. Yeah. So. Yeah. Pruning. The log is
So
used as
an entire branch or.
Pruning might not be used anymore. I was doing some weird stuff. Yeah, that's not used.
Okay.
I had a thing where I was like setting aside this part of the history under certain conditions when I decided, okay, you have these guys who are connected and you have these guys who are connected, and now they've connected to each other, is that legal? When I was doing some crazy shenanigans where this part of the log would be quarantined, and so I was using, it was terrible. It made things, so part of the whole state machine thing is ditching all that crap.
Yeah.
Rewriting the state to make it work better. So the frontier is tracking, okay, you have some graph, and let's say, so this is from Alice's perspective, and let's say you don't have any orphans, because I don't want to draw those. And Alice has done some things, and Bob has done some things, and Charlie has done some things. You can have a frontier, and there's the frontier of the full graph, and then you can have a different frontier. You can say, okay, well, I've done the thing with these two, or I've done the thing with these three. So there's a data structure, there's this frontier data structure whose purpose is just to track part of a subgraph. Basically it's a subgraph, but I call it frontier because I think of it as, the frontier of what's been executed, and it implicitly contains everything that's historically behind it. So for execution, there's an execution frontier. So we're receiving these events, and we have these orphans, and we're doing the synchronization to find the orphan's parents. And then there is a separate execution frontier that tracks which events we have processed, which events have been committed to the network state, let's say. And there's a whole bunch of stuff with that. That's a whole thing. But that's the basic picture. And so if, for whatever reason, if an event is an orphan, then we're not going to execute it. It doesn't even appear when you iterate over the log. It's just kind of shoved off in the corner. You can say, give me the orphans so that you can go then try to synchronize, but it's hidden from the picture. When the code outside that package says iterate over events, orphans aren't shown. So you have an execution frontier, you can remember what you've executed, and therefore what you haven't executed.
And then presumably like very old things, you can just drop them?
Yeah, you could. I'm not doing that. The actual number of log entries should not be big.
Right, because you're just
basically it's the lobby forming, people joining and leaving, and we start ticking. Once you start ticking, it's not building history. Once the game is running, if your set of people I'm playing with is stable, then it's not building new history. Probably. In most cases. So talked about that, I showed that code. Okay, does anybody have any questions about the log? Okay. I want this to end before midnight, so network state. So we have the state. We have a lot of bit vectors and bit matrices. Bit vector, blah, you have a UN64, yeah, I can't have more than 64 peers, don't care about dealing with that right now. Set, clear, blah, blah, blah. It's a vector of bits. Let's just pretend that it's an array of individual bits. Bit matrix is a matrix of individual bits. It does some things, like when you call set, it automatically expands itself, blah, blah, you get a pointer to the array, and then you append, and it's a matrix. You have some number of peers, you get a new peer, you append them to the list, then that gives you an index, you track the index, that index is the bit index into the bit matrix. You have, the bit matrix has as many rows and columns as you have peers. So trusts is a little bit weird. Trust basically comes down to who has had a handshake with who. So the idea of trust is if some random person comes in and starts throwing events at me, I can say, no, I don't know who you are, what this is, WTF. When two people connect, the handshake, which is a whole thing that I'm not going to go over because there's already too much of this talk. The handshake process, you end up with some event that is a squircle. You have Alice and Bob, they have their squircle. That event is one that is constructed by both of them. How I'm doing that? Shenanigans, passing packets back and forth, signing things, it's a mess. But you end up with a connection event that says Alice and Bob connected with each other, and it's signed by both of them. And it has a nonce and blah, blah, blah. So then they start doing things. Alice does a thing, and Bob does a thing, and then Charlie connects to Bob, and so then you have a Charlie Bob event, and then Alice receives that event and processes it and does whatever she does. So trust is basically, have I seen this? Do I transitively have a log of a connection handshake between somebody who's already in this set and this new person? And if you don't, you go, you're inventing stuff, go away. Accepts is the proxy for passwords or whatever the game wants to do. So I'm trying to make this general. The game can decide however it wants to figure out who is allowed to play with who. Steam, friends, public, password, whatever the heck you want to do. So Bob says I accept Alice, Alice says I accept Bob. Yay, we can play games together. So you got a matrix for that.
Why is that not the same as trusts?
Trusts means you have handshaking.
Yeah.
I don't whitelist the connections. I mean, maybe I'll do that in the future, but basically you can connect the game. I guess it's a separation between the separation of responsibilities. The multiplayer engine says, great, you guys, I have a handshake from this person. Transitive or direct handshake. Does anybody not know what I mean by transitive? Cool. So you either have you have a handshake with this person, therefore I know that this person is participating in the process. I know what their key is, what their public key is, that kind of stuff. Accepts, trusts is internal to the engine. Accept is outside of the engine, outside of the multiplayer part. Accept is the game itself saying, this person has the password, this person is on my friends list, whatever the criteria is for, yes, I will play with this person, is accepts. And that's determined by the game. The engine itself doesn't care. It just says, somebody showed up, do you like them? Is that it? No, okay. Running and ticked are just internal things like, are we actively ticking? Have we ticked in the past? The pure state, just tracking the number of bad things that have happened, which don't do anything with, but eventually it's like, oh, you're spamming me with a bunch of bad crap, we're gonna kick you out. Pure state, things like idle, resuming, ticking, pausing. I'm not gonna go into a whole bunch of detail with the state machine because it's already 8 o'clock. But that's the basic idea. We have the state machine, there's an apply method, you get an accept, you get a connect, disconnect, accept, reject. Hey, we're about to start, I want to start ticking, which there's a bunch of logic there, and then I did start ticking, that kind of thing. Pause. Yeah, so there's not that many events. There's not that many things that happen here. So, let's see, talked about that, state versus segment. So this is creating a clear separation between, here is the state of all of the people I know about. Here is the state, the event log compacted, compressed into one state that is easier to query than scanning the whole frickin' graph. And separately there is, what does that mean for me, which I'm calling segment. And the idea is, okay, well, maybe this other person connected, but I haven't said I trust them, or I haven't started ticking with them. So there's, from the current node's perspective, is this, this is in a state of flux, so the actual methods themselves are a bit, but like, is active means basically, can we start ticking, or have we already started ticking? That depends, answering that question depends on which node you're talking about. Alice and Charlie could have 2 completely different answers for, is Bob active, depending on the network state. So there's a clear separation between, here are things I know about the full network that everybody should agree on, and here are things that are relevant to just me from my perspective. To connect, we have events like I talked about. There's connect, accept, reject, will resume, blah blah blah. Talked about that. Every node, a given node has to produce a linear chain. If a node produces, if Alice does this, then we say that's bad. Network state, yeah, talked about that. The state needs to be invariant, needs to not depend on the order in which sibling events are executed. And what I just said, that that state struct, that specific struct, doesn't depend on who you are. Anybody with the same log state has the same network state, or with the same subset of log, same graph subset, arrives at the same network state for the state struct as opposed to the segment struct. Yeah. So.
Can I ask, how does ticking happen exactly? Like, is there acknowledgement? Like,
I'll
how do
talk
you?
about that in a moment.
Okay.
Yeah, it was fun. This is just a joke slide. So, answering your question. Yeah, okay. Ticking, going back to the code. How do we tick? We have so once you have a group who has mutually accepted each other, which mutual acceptance, I'm not doing any kind of 2/3 consensus stuff, it's gotta be mutual, which there's a whole bunch of questions. You can have all kinds of weird causality things. I haven't completely solved that yet. Turns out to be even more complicated than I expected. But in the simple same case where you can say, okay, these guys mutually accept each other, then they say, I want to start ticking. Somebody clicks the ready button. Well, the actual ready button, if you want to be able to unclick the ready button, the game needs to handle that itself. At some point in time, the game says, we're going to start doing stuff. So you have some point in the history that everybody agrees on. It's not literally going to be one event, don't care. And they say, great, it's time to start ticking. So Alice says, I want to start ticking. And Bob says, I want to start ticking. And Charlie says, I want to start ticking. So they issue a will resume message when they decide that they're ready. And then once Alice has seen all of the will resume messages, seen and executed. So once Alice has said, great, I have enough, and I've gotten, there's a bitmap, and it's ticking a little bit box, I'm setting a bit. Once she says my clique, my mutually accepted set of peers is Alice, Bob, and Charlie, and I have a will resume for everybody, great, it's time to start ticking. Alice admits did resume. And once Alice receives, so Alice admits her did resume, and then once Alice receives the did resume from everybody else, once they do the same thing, I'm not going to draw all the lines because it'll get confusing. And once Alice has received these, okay, we can actually start doing stuff. There's a tick number that comes in that, we've agreed, we're running. When the game actually starts running, what happens is you start issuing a different kind of message that doesn't go into the log that says this is what the player wants to do on tick 0. Alice hits the space bar. There's a message. Alice intends to jump, or whatever the heck it is. That's game defined. The engine doesn't care. Alice says these are my intents for tick 0. Bob says these are my intents for tick 0. Charlie says these are my intents. You get everybody's intents. Yay, it's time for a tick. You return that back to the game engine and say, hey, tick.
And you know everybody's here because of this graph and the log in the state machine.
You know everybody's there. You know everybody's ready to start ticking.
But when do you know that your message got propagated to all
You
your
don't.
peers?
Yeah, you don't. Alice says, I got the intents from everybody. I can simulate the next tick. And then she gets the intents. So implicitly, if you get all of the intents for tick n, then you must have received, no, that's not entirely true. Basically, if there's something missing, if Alice says I want to do tick 2, and she doesn't get that message, then the game engine goes and says, hey, Bob, what do you want to do for tick 2? Hey, until she gets a response. Or until some threshold is crossed and he says, meh, Bob's gone.
But that threshold is in this log and detected by this.
For the ticking, no.
Oh, okay.
Once we start ticking, the log establishes who is ticking. Once we start ticking, it becomes a lockstep thing.
So each peer broadcasts its current event a tick, and the others, if they receive it, great. Otherwise, just keep going.
Yes, so the game, the engine says, we're ready, back to the game. The game says, great, tick. The engine says, hey, my node is ticking. Broadcast that to everybody. Waits to receive the messages from everybody else that I want to do, that everybody else is ready to execute that tick. Receives all those messages, goes to the game, says, hey, we've got here are all of the things that all of the players want to do for tick 1. Game simulates tick 1. Returns a hash of the actual synchronization and consensus on the game state is a to do. But in theory, game executes, gives back a hash that allows us to ensure that everybody actually simulated the same thing in the game. And then also says, here's, press the spacebar, press an arrow key, and that gets broadcast.
So you're saying it's each tick you broadcast to all the peers, each peer broadcasts to all the other peers, so it's n squared. Like there's no leader, no centralization.
On each tick, each peer says to every other peer, here is what I am doing right now.
Yeah, so it's in squared communications at the ticks.
Yes.
In squared or broadcast, but presumably in squared.
Each tick broadcasts and messages. Or each peer broadcasts and messages.
It transmits in messages.
Yeah, so the total number is n squared.
So since there's no sequencing.
Once you're ticking,
tick, how would you deal with the conflicting intent?
once we've done this, now we have a clock.
Yes, there is a sequence of
No,
tick.
but say the same tick. Alice says, I want to occupy coordinate 2, 2. Bob says, I want to occupy coordinate 2, 2. And then
That's the game's
Charlie
problem.
says, I see both guys trying to occupy 2, 2. Who actually has the coordinate 2, 2?
It's a game's problem. The multiplayer engine says, so the way I am writing the code, what the multiplayer engine is transmitting is a abstraction of the keyboard inputs, of the inputs. So what Alice transmits is the human at the keyboard hit a key.
Right.
And there's a translation, spacebar becomes jump or whatever. So if you have a game where everybody has squares and you can only have one person in a square, then which person gets to occupy that square, however that conflict is resolved, is the game's problem. The multiplayer engine doesn't try. The multiplayer engine basically says, here's the keyboard inputs that everybody had. Do stuff.
So the analogy here is that this log and the state machine and all that stuff left of tick 1 is everyone sitting down at the table.
Yeah.
And you know who's at the table, and you're not worried about people who aren't at the table because they're not playing the game. And then you take turns, you all play your card or whatever. But you're not worried about, you're not waiting on, that guy wants to play the game, but he's not sitting at the table yet. You've resolved all of that. So there's everybody sits at the table, and then there's the playing the game.
If David shows up,
Yeah.
there's a whole dance.
Yeah.
This stuff happens again. Basically, David is stuck sitting at the side table until everybody else agrees that we're all ready for David to come back in. You go through the accept, and once David has been, so you have your current ticking group, you have your ABC, and once ABC mutually accepts David, has to go both directions. Once that has been achieved, then David transitions into the intermediate. I am ready to start playing. I have been accepted into the group. I'm now in, not ticking. I've got to get ready. And that's where the state synchronization, the game state synchronization happens. That's where we start transmitting a snapshot of the game state. And once David has completed receiving that snapshot, has replayed, and then That snapshot is timestamped, so we know that that snapshot happened here. And so then David can say, great, all of these other things happened. And then David, I don't 100% remember how this code works, but basically David comes in at some point. You know, we have some tick where David has synchronized, and David goes, great, I can start actively participating. And to arrive at the state for that, he has to replay all of the things that happened in between, all of the intents, and tick the game without him in it for all of the ticks that happened between those 2 points of time. That process has been a major source of headache. And then you have fun things like, what happens if that happens in the middle of the resumption process?
Right, but on that conflict resolution though, I don't think you can actually sidestep that problem, because if the resolution is non-deterministic, as the observer, you can end up with the wrong solution.
So the constraint is basically everybody, at that point in time, we have established that these are simultaneous.
Right.
And everybody must have this full set. So as long as the conflict so you're synchronized, everybody knows everybody else's intents. That means the game's conflict resolution process needs to be deterministic across those set of
But if there is, if there is no leader, no acknowledgements, and you just broadcast everything, how do you know that you are actually synchronous? Like, what happens if there's a network partition? What happens if a subset of the nodes is isolated from the remaining nodes?
If there's a bad enough network partition, then probably the game falls apart. If you have a partial network partition, if their dog ripped out their Ethernet cable, then everybody else is going to agree this person has stopped responding. We're going to kick them.
No, you have some people in the US in the East Coast, other people in the West Coast.
Yeah.
US East is isolated from US West.
Shark bites through fiber optic cable going across the Atlantic.
Yeah. And you have no notion of quorums or majority or acknowledgements. Like, how do you deal with that?
I haven't.
Okay.
And my strategy is, this is a game, so it just has to be good enough.
But you do know all the players.
Hmm?
You do know who all the players are.
Yes.
And so it's easy to tell that you haven't heard from this person.
Yes.
Rather than, I don't know,
Now,
some new
if you
packets
have-
coming in and you're like, oh, who's this?
I mean, I don't want to minimize the issue, because if you have some weird networking partitions where Alice can talk to Bob and Bob can't talk to Charlie, and you got some crazy stuff going on, it's gonna get weird. And there's probably, like, I'm building a system, I'm not doing a quorum, I'm not doing the leaders, so there's probably scenarios where it just collapses. But as long as it works 95% of the time, as long as it works like 99% of the time, it's a game. I'm also not trying to do Counter-Strike.
Yeah.
I'm not trying to do a competitive, Fortnite, I'm not trying to do a competitive multiplayer. This is not designed to be, if you want to run Counter-Strike, Fortnite, have a server. This is not for that kind of game.
Yeah, because you haven't dealt at all with like cheaters.
Yes.
Yeah.
So, if you want those kinds of things, there are way better ways to do that kind of game than this thing. So I'm not trying to solve every problem. I'm just trying to make it work under typical conditions. As long as the game continues running and operating under typical normal network situations, that's my target. If you have somebody playing in London and somebody playing in Los Angeles, yes, I want that to work. If you have two people playing in the US and two people playing in Europe, and a shark bites through the fiber optic cable and their games just disintegrate, I'm not going to try that hard to solve that particular problem, unless the solution just kind of falls out. Because your game disintegrating because shark bit through the cable shouldn't happen. That should be a very anomalous event, and the stakes are low. I'm not going to try to solve that. And the conflict resolution in the tick, the game has to decide. The game has to have a deterministic way to say, these 3 people clicked the arrow key to go into the same square on the same tick. I need a deterministic way to do that. Now, you will have IDs. The game will have the public key hash for each party, and it knows here are the parties who are ticking in this tick. Here are their intents. The game could just do sorting based on the key, based on that hash. So there's plenty of ways to do deterministic conflict resolution for the intents. One thing I would mention, that resuming, that whole thing, like if Bob, if the late, I call them late joiner, somebody who joins either after ticking or when we're trying to resume ticking. If the late joiner happens in the middle of the resumption process, basically you have a frontier. Well, yeah, you have a frontier and you say, this is the frontier I've executed. As soon as you see a will resume from Alice, you stop executing Alice's events. So if Alice says will resume, accepted the late joiner, you don't process that until later. So Alice said we're going to resume. Any future events from Alice are not processed until either you hit the boundary, everybody resumed, or you receive a did resume from somebody else. You have an arrow like this. So we have our starting point, and Alice resumed, and Bob didn't do anything, and then Alice accepts the late joiner. If you see a resume from Bob that has this as its parent, then you execute this. So once Alice has resumed, until you hit that boundary, nothing else from her gets executed unless you have this causal relationship. Then you execute those. And then anything that comes after you don't execute unless you get another. That gives us a deterministic way, regardless of whatever messages people are emitting, to say, great, we're at this boundary, we all need to agree to resume, and we're not going to execute anything that happens unless we have this causal relationship until everybody's resumed. And then once everybody's resumed, you say, great, I'm now going to start ticking. You do the did resume, and that has the, I mean, it will definitely have a parent from all the resumes. I think that doesn't have its own boundary, because then you transition into the I'm currently ticking. And when you're currently ticking, you stop executing log events, except when Alice says, I want to tick, when Alice says, hit the keyboard for tick 3, that network message includes Alice's current log frontier, the frontier of all of the messages that are not orphans, all the events, the log events that are not orphans that she's received. And then she waits and sits, does nothing until everybody else, until she gets the tick intent from everybody else. Once you have the tick intent from everybody else, then you take the union of all of their log frontiers and then execute up to that. So that means this is not getting processed. This is not getting executed during ticking until you get everybody's picture, and then you execute up to that point, which means everybody is executing the same set. So once you start ticking, the network state evolves in a synchronized way, and if you have a late joiner come in and you start accepting them, you have a deterministic way to know when they should start ticking.
Yeah, nice.
Which was hell to figure out.
I really like how you
Pieced it together.
yeah, because like TCP is reliable enough, but TCP is made out of UDP, which is unreliable, and you've got the same sort of thing here, where you end up with a ticking of, a synchronized clock, but you've only built it out of not synchronized parts.
And then you get network partitioning during the accept phase. So if you have, it's like if you can have a scenario where, so rolling back, we're not ticking, ignore that. if you have ABC, you have Alice, Bob, and Charlie, and if Alice accepts Bob, I'm going to use these arrows to mean accepts, and Alice accepts Charlie, but there's nothing between these two, and you decide you want, Alice says, I'm going to start ticking. With who? You have a mutual accept here, you have a mutual accept here. It's not even, forget what the term is, but when you have a complete network partition, and these, they're completely separate.
Split brain.
You don't have a split brain. You don't have faction wars, you have a love triangle. And Alice doesn't know who to tick with. I've reworked incrementally to make sure I didn't break everything in the middle. The network struct like 3 times, evolving it to be less and less and less having anything to do with whose perspective you're executing from. I think there's still a little bit of stuff, I said, oh, the network state doesn't depend on who you are, it only depends on, that's kind of a lie. I'm getting there, it's aspirational. And eventually I will reach the point, but then apparently there's actually like, you don't have any definite answer. If Alice starts ticking, then okay, well then the I want to tick with has to include who you want to tick with. But then if Alice's game says, yes, I want to start ticking, then you have to decide who you want to tick with, which maybe means Alice can't decide to start ticking, and so she has to wait for a message to come from one of the other two. That's not solved. Hopefully I'll get there.
When you talked about frontiers, that's sort of you're talking about some sort of like hash.
I'm just talking about the graph. So you have
Is a frontier a node in the graph, or is it?
It's a set of nodes. So
Isn't that a merge?
Ish.
Okay.
It's an implicit merge, let's say. And the circles, and I just don't feel like drawing other shapes because I'm bad at it. So at this state of the graph, these two are what I'm calling the frontier.
Yeah, why isn't that just another node with both parents?
Because
why isn't it a merge commit?
Because nodes are signed, and if two different nodes, if two different peers have this same state, then either we have to give up on that merge being signed, so the merge is an unsigned graph node, or each peer generates a different merge, and we end up with Alice having this merge, and Bob having this merge, and that means that every merge generates a profusion of history.
Yeah.
And so I looked at that and I said, well, I don't want that. And I looked at the unmerged nodes and said, this sucks. And so my conclusion was, meh, we're just gonna not have a merge until something happens.
Okay.
So when Alice does a thing, that generates a merge.
Yeah.
The next thing that Alice does will generate a new node that inherits that frontier. But I don't actually merge until that happens, because honestly, not having a single point at the end doesn't really hurt. It's not that much of a problem. This network state.
Yeah, you just have to agree on the sort of rightmost nodes.
Yeah.
But what you're saying is that if you had a merge commit, the parents would sort of, or the hash of the frontier would sort of would be the data in the merge, not the merge node itself. I understand.
Okay. And that's part of the frontier, but the actual frontier struct. So there is the frontier of the whole log. There's the frontier of here is everything that I have minus orphans.
Mm-hmm.
Then there is the frontier struct, which is basically a subgraph. So the actual frontier struct, what it's doing is it's just tracking a substate. And so the frontier, that struct is used for things like what have I executed. So in the cases of we're currently actively resuming, and we have to do these boundary things, or we're ticking, and we might get events, but because we're ticking and because we need to be synchronized, we can't actually process those yet. We just have to shove them in the log and forget about them. The execution frontier tracks what we have processed. And so that is its own thing that says, okay, so then that gives us a nice straightforward answer for, okay, when we add up all of the tick messages, we have this frontier. And I can look at those two and go, great, I need to execute those two. And I can also say, oh, these have a defined topological order, so I'm gonna topologically sort and execute those so that they execute in their causal order. Any other questions? Hopefully not, because we have 5 minutes left.
Yeah.
This is all what you put on a code word in the Loki?
Yes. I'll put a new reference to that. Also, anybody who wants to know more about relativity,
Oh, yeah.
Yes.
has great videos. Cannot recommend them more. He also made this weird, insane metal thing where you can do the world line stuff and you're shifting things around and it does this insane, like, screw, it's like, you don't just rotate the thing, you do the rotate squishy. It's great. I love that. If you wanna maybe kind of a little bit understand relativity in physics.
Has anybody tried Fable 5?
I have not, because it's gonna use up my usage way faster.
Yeah. I had a coworker who tried it, first thing last night, when they opened it up or whatever, and, it did not finish the one
Because he
prompt
ran
that
out of
he did.
tokens?
He ran out
What?
of tokens on his pro account with the first question he asked.
Oh my god, okay.
A lot of the folks I'm working with that have been testing it, it's already been getting gated responses because they're trying to stop effectively DeepSeek version 5 from being distilled out of Fable.
Yeah.
So any of the training or eval loops that you could have done with Opus or Sonnet, the other ones, it's just politely say, I'm not doing that for you. So I think the rails that they put on it are way beyond the
Too restrictive,
cybersecurity and it's more on the keeping the proprietary elements.
It won't talk about, if I'm remembering the story right, it won't talk about chemistry, it won't talk about biology.
Or any AI stuff, basically, like LLM.
Yeah,
Any of the
big
training
categories.
specific components, they're blacklisted, so.
I mean, since, for me personally, so we use Claude at work, but since 4.6, I haven't noticed a difference. Like 0.7, 0.8, I don't know, it feels pretty much the same.
Opus or whatever?
Yeah.
I feel like 4.8 is worse than
4.8.
Yeah, I still use 4.6, yeah.
Losing its mind.
Yeah, can't stand it.
Oh, yeah. So, in, July, hopefully, I'll have, I've got an idea for something we can be talking about, but, you know, if you've got ideas.
I'm down to give something to give a
Yeah,
talk in July.
by all means, by all means. August will be, is it during GopherCon, I guess? Cause I think it's right after DevCon, so during GopherCon, I think.
Where is GopherCon?
Seattle.
Yeah, I don't.
I wanted to go to both, and that would have meant flying from Austin to Seattle to Vegas to Austin. And now I'm going to visit friends, and that would have involved flying from Maryland to Seattle to Vegas to Austin.
Yeah.
Not happening.
Is Go 126 coming out soon?
What,
27?
27?
27?
Yeah,
Isn't there some new cool stuff in there, like?
Yeah, I don't know what's coming.
Generic methods?
Yeah,
generic
yeah.
methods, I don't know. I'm not sure about that one yet.
They're doing generic methods, but generic methods cannot satisfy interface.
Correct. Yeah, because of generic methods satisfy interfaces, you have to have weird dynamic code, runtime code generation or some kind of hacks to get around
And the
dynamic
compiler
code
is
generation.
really slow.
Well,
I mean, you could do JIT.
It's the
But-
compile time constraint check is the one they can't do a lot of things, that's
Well,
the biggest constraint.
It's beyond that, if you have a generic method with an unbound, so if you have, if you can have a generic interface method. So if you can satisfy an interface with a method that has a generic parameter, then because of things like reflection and plugins and other stuff, you cannot guarantee at compile time that you know all of the possible instantiations for that type parameter that it will be called with.
Yeah, it's the structural typing constraint.
Oh, because of plugins. You effectively haven't seen all the source code yet.
You cannot guarantee that you have seen all the source code.
Yeah.
You cannot guarantee that you can accurately statically so Go is flexible enough that you can't guarantee that you've accurately statically analyzed all of the potential call sites.
Is there anything that cannot be pointed out as a compile time problem, they won't include it?
Now, there are ways around it. You can do get, another one you can do is you can say, okay, for anything that is pointer typed, as I understand it, you can write a functional implementation of, or instantiation of a generic function that will work for arbitrary pointer types because of constraints like you can't access fields. You can't access struct fields, so you don't have to deal with offsets. So you say this struct has the, you say I have a generic method and it has a type parameter, and that type parameter has these methods, so you can generate a dispatch table such that arbitrary pointer types can be passed to it.
But I think that still end up being a runtime resolution, which that's.
I mean, runtime resolution is acceptable. So there's if you have some interface like io.reader, the runtime already has to be able to dynamically construct the method table for type X being converted to interface.
But yes, but the binding is done at compile time, because that's how one of the is say the generics, existing generics, certain thing when you were given, I forgot what it was, it will tell you ambiguity of type is because it could not resolve to a solid type of compile time. Then that particular use of generics is not allowed.
So I think there's two things going on. There's one, there's dynamic dispatch. So static dispatch is we know X is int, struct, myint, whatever the heck it is. We know what it is. When we emit the code, we can emit a direct call to that address. There's indirect dispatch, indirect calls. If X is io.reader, if X is an interface type, then call sites of x.read have to go through a pointer lookup, have to go through a dynamic indirect call process where they say, what is the at runtime, what is the concrete type of X? What is the pointer for the implementation of x.read for that concrete type? And that table, the table that you use to do the indirect, you have OS file, and it has a read method. So, and then you pass in a file to a thing that takes a reader, and then you call rd.read on that, x.read on that thing. At runtime, that is a indirect function call. That's a pointer lookup and then jump to the address. The table that it uses to do that indirect lookup sometimes has to be generated at runtime. So when you pass your file into the thing that takes a reader, if there is not already the OS file as reader lookup table, sometimes it has to construct that lookup table at runtime. And that is a constraint that the existing system has, which comes down to a similar thing with the generics where you cannot, it's impossible because of reflection and pointers and stuff to statically guarantee that you have identified all concrete types that ever get passed in this function as a reader.
Right, but not
That's why you have a type select.
concrete.
Or a type, what's the
assertions and stuff
yeah,
like that.
type assertion, yeah.
I mean, the interface methods are the bigger problem. Calling a method on the interface type variable.
But I think that at least for generics, the reference of the generics actually gets replaced by the concrete type at the compile time.
Yes.
So that generic is really just an illusion.
Ish.
It doesn't really exist, it's just more of a syntactical sugar.
It depends on the garbage collector shape,
Right.
which is a weird thing that I don't totally understand. But the point is, if you have foo that takes generic type T and has a parameter X of type T, then when you pass in my struct star my struct, can't remember right now. When you pass in a struct pointer, when you pass in an int, it gets instantiated with int. So it actually emits
Yeah,
a
basically,
version.
the compiled code is no longer have generics there.
Yeah, so the generics get compiled out basically, and you do it with int, and you do it with float, and you do it with string, you have 3 different versions. If you do it with A star and B star and C star, you have 1 version. Every time you pass in a pointer as t, that ends up being the same concrete, I think, pretty sure, ends up being the same concrete instantiation, which works because generic functions cannot access fields on generically typed variables.
Right, because they're actually an embedding, not a.
Well, so you can't access fields partially because it only emits 1 version of it. It doesn't emit a separate version for every different pointer type, which means you can use tricks like jump tables. So you have basically, if you have type t, if you have your type parameter t that is constrained to be some type that has a certain set of methods, as I understand it, that creates an implicit interface. And all method calls go through that implicit interface, and they go through the dynamic dispatch process for pointer types.
And because it's an interface, you can't access fields. You can only access methods on that type.
Because we're doing these shenanigans, where we're using these jump tables, offsets, so you actual struct, you have all these fields, you have to have the address relative to the address of the field relative, the offset relative to the address of the whole thing. To avoid needing the same kind of multi-pointer lookup shenanigans for field offsets, they just don't let you use fields, I think. But if it's a concrete, if it's a non-pointer type, if it's a value type, that all goes out the window. And you have a
Just
different.
because of the indirection of the pointer.
Well, I think it was basically a design decision. So you could do fun things without having to do that. Like int, float, you could have a min-max. I mean, we have built-in min-max now, but pretend we don't. Or, invent some other function that can do that. So you have min-max, or you have a min function for parameterized on t, where t is some type that supports less than or greater than, and you have ABC of t, and you return the minimum one. Right now, passing in int, float, uint gives you 3 separate copies of the machine code. One that works for int, one that works for float. You could instead emit a single one and have a lookup table for whenever you have operations that depend on the concrete type of those parameters. You call into this lookup table and execute this piece of code. That would work. And that would work I think that would work for generic methods. But they don't like it, basically. The response I got when I suggested things like that was essentially, we don't want to. Not this doesn't work. Not that there's a fundamental flaw, but
I'm still not really sure what it's for.
generics.
No. Yes. But even more so. Like I haven't. Maybe I haven't been looking hard enough, but I haven't run into a problem where I'm like, oh, if only I had a method.
I mean, sorting,
So,
comparing.
I just wanna say, we got half a margarita pizza, a quarter of a cheese pizza, another slice of
You get to
jalapeno, and pineapple and pepperoni back there. And we've got some more drinks. We do need to get out by 9, including all cleaned out, so let's aim for a couple more minutes.
TLDR, everything that you can do with the non-interface satisfying method, you can do with function. So you could just use generic functions for everything. But that makes your code awkward.
Yeah.
So in terms of expressibility, readability, when I look at this code, how easy is it to understand what it's doing? Generic methods can make things easier. Can make things cleaner and more readable. That's
Anybody
fine.
else need code?
Yeah.
We've had a few people a couple times forget to get them. And then panic, come back up. Yeah. No, you press not 3, yeah.
How much is the parking without it?
It's about 50 bucks.
Oh,
Or 3 hours.
As opposed to $8.
That would depend. So it's
Yeah, it
3.25
depends.
every
Yeah.
20 minutes.
Yeah.
So it's basically $10 an hour. So when did you park?
I Ubered.
Yeah, that's the way to go.
So if you park at 6 and you leave at 9, then that's $30.
Yeah.
Or you get that and it's $8.
It tells you, by the way.
How much you would have paid.
Yeah.
Yeah.
I think.
No, no.
Pretty sure it does.
Yeah, I've been here from 5 until 10:30 before, so yeah, that's upwards of $50.
I know more money on the garage than the hotel rooms.
I don't know, these are pretty expensive hotel rooms.
Yeah, sure.
Good presentation. Thank you.
Thanks for coming out.
Yeah,
and,
thanks for organizing.
Yeah, thank you. And we'll see you next time, man. Feel free to take as much pizza home with you as you'd like. We got a little bit of cheese, margarita, half a margarita, and then a sliced something. So yeah, take it with you if you want. Otherwise, we're throwing it away.
I guess
We are throwing it away.
I'm sure somebody will probably eat them.
Yeah.
Or I'll throw them away at home. Shouldn't be surprised, but I wasn't. For some reason, I was not anticipating spending that much time answering questions in the middle of everything.
Yeah. I was thinking, oh, this will be a quick one, and then I was like, no. Once I heard the first couple questions, I'm like, oh, this is gonna take a while.
Can you need any help with anything else? I guess we're all cleaned up now. Whew. That was a marathon talk.
The thing is, I want to not be the source of the problem. Like it's kind of beyond our ability at the moment to like make this place super clean because of like everything. I don't want to be the one to be the source of the problem. So pizza bones on the ground is not something I'm cool with.
Pizza, don't you mean crust?
Yeah.
Do we have?
Yeah, there's.
I'll go stack up with that. I'm sorry.
Yeah. Oh, wasn't not us. Sandwich. Hello. Just hello. I wish you could on top of the trash can. Well, it's definitely cleaner when we're leaving it than we got here, so that's for dang sure.
That's a good quality to be remembered for.
Yeah, I know that Elijah and the new gal were coming in here earlier to check it out, and we're like, what the fuck? and we're, yeah, because we're over here like cleaning it up, and they're like, we told them. This is the second day in a row we told them. Hey man.
So they work for the.
Yeah, Elijah's the guy that brings the stuff and runs all that. And so he and I'm guessing it's the new gal or whatever. We're coming by. Yeah, it's all right. It's all right. Shit happens. We've definitely been in situations where we had the GTFO and didn't leave things as clean as we would have liked. We were pretty good about it, but have not batted 1,000 on it.